This is forces in multiple objects, or in other words, whenever we have problems with multiple objects, and we should draw a free body diagram for each object, and we'll write corresponding equations of motion for each object, and then just solve them. So I'm going to jump right into a problem here. Imagine we have two objects, mass 1 and mass 2. They're touching, they're next to each other, they're on a frictionless surface, and we start pushing against them to the right with a force F1, with your finger, just imagine pushing them. And before we start solving any questions, we want to draw free body diagrams, and that's what I've started writing over here. There is going to be acceleration. So because there's no friction, these things will accelerate, and they're going to accelerate together. And mass 1 is 5 kilograms, mass 2 is 25 kilograms, and the force F1 is 135 newtons. So go ahead and pause the video and write what you think are the free body diagrams for these two objects. And when you're ready, we'll go ahead and continue. So I'm going to start with, let's see, mass 1. Mass 1 has a gravitational force, and normally we write mg, but we have two masses. We have mass 1 and we have mass 2, so we want to be specific and show what the gravitational force on mass 1 is. It should be mass 1 g. I don't like the way I wrote that. m1g. And of course, mass 2, which, should have a larger gravitational force because there's more mass here. We should label this as m2g. Okay. The surface is putting an upward normal force on both of these. Should be equal to their respective gravitational forces. Now, normally we just write Fn, but these are going to have different amounts of forces on them. So we wouldn't just write Fn, we would say, let's say Fn1 and Fn2. If we can't use Fn for both because they're technically different quantities, they're different amounts. And so, yeah, you don't want to show that those are equal by writing Fn for the same one, because then when we solve a problem, we can't assume that they're the same. They're not the same magnitude of force. So we have to specify this is Fn1 and Fn2. That's pretty good notation to use. Okay. Mass 1 should have a force to the right, F1. And let's think about M2. M2 is getting pushed, is also accelerating to the right. But it's not that force F1. Your finger is pushing on mass 1. But what's pushing mass 2 is not your finger, F1. It's not your finger with force F1. It's actually a force from mass 1. So could come up with your own notation for this, but it's a force from mass 1. So, you could say something like this. But honestly, the one that I use and the one I think you should use, the one I think you should adopt is we say the force of 1 on 2, the force from mass 1 onto mass 2. But I write it kind of quickly and I just say force 1, 2, force of mass 1 on 2. So the force that mass 1 is putting on mass 2. And don't say F12. It's not F12. It's force of mass 1 on mass 2. And we're almost finished here. There's actually one more force we need to account for. So again, kind of just think about it. And this goes back to Newton's third law. If mass 1 is putting a force on mass 2 will simultaneously exert a force equal in magnitude, but opposite in direction on mass 1. So I didn't draw them quite the same length, but they should be. And you could call it F12 because it's supposed to be the same magnitude. I like to write the force that 2 exerts on 1. And of course, these two forces are equal. So the force that mass 1 puts on mass 2 is equal to the force that mass 2 puts back on mass 1. And that looks pretty good to me. I think we're good to go there. Now, question A is, what is the acceleration? They're going to have the same acceleration. You push on 1, and mass 1 is pushing on mass 2, and you're pushing them together. They're going to accelerate together with the same acceleration. And so the next thing we need to do is figure out which forces are contributing to that acceleration. And really, we're looking at the horizontal forces. The horizontal forces. For this situation, we don't care about basically the normal force. We know that Fn1 is equal to m1g, and Fn2 is equal to m2g because there's no acceleration vertically. So we're going to write two equations. The sum of forces is equal to m1a for this free body diagram, and the sum of forces equals m2a for this free body diagram. So two separate equations. And really, we have three equations. Don't forget about that one. So the forces that are relevant to the acceleration of mass 1 is F1 and F21. Now it's accelerating to the right, so we should put F1 first, and then it's accelerating this way, so that's the only force we need to put F12 in this equation. So let's write that. It's F1 minus F21, F of 2 on 1 equals M1A. And over here we would write F1 on 2 equals M2A. Cool. And let's plug in some numbers to see what we're working with here. This is 135 minus F21, which we don't know what that force is. We don't know how much that force is, equals M1, which is 5 times A. Okay, I'm going to be very careful and write this as really as a subscript down here. I almost get into that bad habit of writing the subscript a little bit too large. And clearly we have two unknowns in this equation. We're kind of stuck. Over here we'll continue. We know mass 2 is 25. I'll do that. And this is A. And again, we have two unknowns. We can't proceed. And so the trick for these types of problems is we're going to substitute. We're going to take what we know about force F1 equals force 2 on 1. And so in other words, this force and this force are the same force, the same magnitude of the force. And so we're going to take this expression here and we're going to plug it into this equation. This is not something you need to show me. It might be good for your notes so that you can remember what we did here, but it's not something that we need to see on a quiz, on a test, or any of that. So I'm going to say minus 25a equals 5a. Let's put a on one side of the equation. I think that's plus 25 plus 5, that's 30a. And so we just divide by 30. And we just plug this in the calculator. So 135 over 30, your calculator will give you a result of 4.5 meters per second squared is the acceleration. Cool, so that's part A. That's the acceleration of those objects. Question B, I want to know, what is the force that mass 2 puts on mass 1? What is this right here? And we already have a good expression for this. This one is F12, but that's the same as F21, so I'm just going to rewrite this. F21 is just 25 times A, and we know that we know that A is 4.5, so we can just substitute that, and we will multiply. We should get a result of 112.5 newtons is the amount of that force. That's A and B. So we're using some techniques that we've kind of used before, this substitution technique into these equations. But of course, there is something new here with using two free body diagrams. There's another method that we can use, easier method to figure out A, although that we can't use to figure out the force of mass 2 on mass 1. And the simple way to figure out what the acceleration of these two objects is, a little bit faster, is to think of it as a system. In other words, just consider mass 1 and mass 2 to be one thing. And so what I mean is, what if we had a free body diagram that looked kind of like this? We had one object with a combined mass m1 plus m2. So there is a gravitational force of m1 plus m2g. There is a normal force, which, since this is the only free body diagram here, we can just call it Fn. And now we're pushing this with a force F1. It's a little tricky connecting all these lines with this pen here. So anyway. And so if we want to figure out the acceleration of the system, which is mass 1 and mass 2 combined, then the only force we need to include is F1. And so let's write that again. The sum of all forces equals m1 plus m2a. And so we'll substitute that force F1 equals m1 plus m2 times a. I'm still getting used to writing on this thing. And so I don't like it when my handwriting gets a little sloppy here. Cool, and I think we know enough now. So F1 is, what was F1? It's 135. And mass 1 plus mass 2 equals 30 times A. And of course, we're getting the same result that we got over here in this expression. 135 equals 30A. And so we're going to get 4.5 meters per second squared again. So look at how short this is on this side compared to what we had to do over here. So I will say this, you need to know how to do the problem the first way we did it. Basically everything that's on the left side here. Everything that's on the left side. The two free body diagrams, the two equations. Because you need to be able to solve for this force F2 on 1, something we would call an internal force in this system. Those two internal forces between those masses would cancel, and so we don't have to include it on this free body diagram. But doing it this way, we don't have that information, so we can't figure that out. So technically, the left way, in my opinion, is better because it's more thorough. But if all you're doing is figuring out the acceleration, you can use this, system method and kind of do it that way to figure out the acceleration much faster. Okay, but again, for quizzes, tests, AP exam, you got to know the left side. Okay, is there anything else? I think we'll just continue on the next one. The next problem involves an Atwood machine. This is basically a pulley which is a wheel and it has a rope on that wheel and it can turn left and right, uh, clockwise or counterclockwise, in other words. The pulley is fixed at the center, so it won't move. In this particular problem, we're going to say that the pulley is massless. In a couple of weeks, um, we'll kind of see why that makes a difference. But okay, so we're going to say that the pulley is massless. The rope itself is massless. And the simple reason for why that is massless right now is because we're working with a mass 1 and a mass 2 down here. And having a pulley with mass would kind of change things from what we're showing you here today. Okay. And the rope is inextensible. In other words, it won't stretch. Yeah, it won't stretch when it's being pulled, that sort of thing. It's a fixed length rope, and that length will not change in the problem. So mass 1 is 21 kilograms, and mass 2 is 3 kilograms. So imagine this rope, and at the end of it, we'll attach some weights to it. And the pulley is free to spin, left or right. Clockwise or counterclockwise is really what I mean. And we have two questions. What is the acceleration? And what is the tension in the rope? And so my question to you is, before we get started, is will this machine, they call it, but will this pulley, will these masses accelerate? In which direction will they accelerate? And let's start there. So, you can pause the video and think about it. If you have these two weights on here, I'll give you a hint, it does accelerate. Does it spin counterclockwise or does it spin clockwise? Anyway, so here's the answer. Mass 1 has more mass, 21 kilograms versus 3. So it will accelerate in this direction. This mass will accelerate in this direction. Now, we can call that A1 and we can call this A2. And my question to you is, which one is greater, or are they the same? And you can pause it and think about it. When you're ready, the answer is that they're actually the same. So we can actually just call that A. And the reason is that rope is inextensible. So if mass 1 starts pulling on that rope a certain length, it pulls on the rope a certain length, well, that length up here must also go up. And so mass 1 accelerates, mass 2 will have the same acceleration, just clearly it's going to have to go up, whereas mass 1 falls down. Okay. So let's continue. Let's draw some free body diagrams for these. Let's say this is mass 1, and this one is mass 2. I'm not being very careful about drawing the sizes of them. I don't think that really matters. Let's put gravitational force. This is M1G. Let's put a gravitational force. Should be less, so I should make that smaller. M2G. Drawing the lengths proportional or nearly proportional is pretty important. And pulling this one up is a force Ft. And pulling this one up as well is a force Ft. Now, it's late at night and I'm not thinking very much about these, but let's draw them accurately. If mass 2 is going to be going up, that force needs to be bigger. And if mass 1 is going down, M1G needs to be bigger than Ft, but ft is the same for both of these, so I'm going to draw them the same length, which means that I need to draw m1g a little bit longer. How's that? Not bad. Okay. What's next? Let's write some equations for these. By the way, I like to draw a little arrow showing the acceleration. Helps us write the equation. Sum of all forces equals m1a. And over here, the sum of all forces equals m2a. So let's write this equation. This is m1g minus ft equals m1a. Over here, ft goes first, minus m2g equals m2a. Cool. Now let's look at what we have here. We have mass 1 is 21, we have g, we don't have ft, in fact we want to figure that out. We have m1, but we don't have a. So this is going to be a situation where we have two unknowns, and the same thing will happen over here. We have two unknowns. Now, if we want to solve for a, and we don't have ft, we're going to substitute ft. Because essentially we want to get it out of the equation so we can solve for a. So let me just show you. What we're going to do, I don't know, I think I like this method is we're going to say ft equals m2a, and we're going to add m2g to this side of the equation. And so now we have an expression for ft, and that expression for ft doesn't, of course, include ft. And so that will not be there. Now, when we substitute this, use parentheses, and this is a big mistake. Or I should say, this is a common mistake that I see students make. Let's do it this way. Like this equals m1a. Sorry, my equations are kind of taking up the space here. Let's do it like that. Cool, let's distribute m1g minus m2a plus minus m2g equals m1a. Let's get g's on one side, let's get a's on the other side. m1g minus m2g equals m1a plus m2a. We want to create an expression that isolates a. So how do we get a by itself on this side of the equation? m1g minus m2g equals m1 plus m2. In other words, we are factoring out an a out of the expression, but I'm putting the a in the back here. And then to finish this off, it's m1g minus m2g over m1 plus m2. Do not cancel out m1 and m2. You can't do that. Equals a. Let's go and insert some numbers here. M1 is 21 times g, so that's 210 minus 30 over 21 plus 3, that's 24, equals a. So that looks to me like 180 over 24, and that comes out to 7.5 meters per second squared. Okay, is the acceleration, which they both share. This one accelerates downward at 7.5 meters per second squared. This one accelerates upward at 7.5 meters per second squared. Cool. That takes care of A. Let's figure out what Ft is equal to. That's part B. Ft equals, okay, it's m2 times A. So that's 3 times 7.5 plus 30. And that looks like it's coming out to 52.5 newtons is the tension in that rope. And of course, it's, like we said, it's the same tension. Cool. Now let's look at the shortcut. So if we look at it as a system, and here's how this kind of works. Because they are going at the same acceleration, because m2 is going up with the same acceleration as m1 going down, we can think of them as a system. And the sum of all forces on that system is m1 plus m2a. We're trying to solve for a this way. And so we have to think about what is the force that is contributing to that acceleration? What is the driving force here in that situation? So if you look at these, why is it that it's going down this way? And that has to do with the weight, m1g, of mass 1 is the driving force pulling down. Is there any force that opposes that motion, that acceleration? And the FTs here kind of cancel, so clearly it's the m2g that kind of opposes that acceleration. So we're going to subtract that one. Those are those two forces equals m1 plus m2 times a. And of course, m1g minus m2g over m1 plus m2 equals a. Well, this looks a lot like this over here. And so we get the same result looking at it that way.